Alright guys, so we're going to work on this problem, determine the fourth roots of unity and plot them on the complex plane. Now, we know that unit means 1. Okay, so I've got this 1 in brackets here. So we're basically looking for the fourth root of 1. Okay, now again, we could think if this is just a real number, what number multiplied by itself 4 times gives me 1? Well, 1 times 1 times 1 times 1. So the answer would be just 1. Now, if we're just talking real numbers, then that would be our solution. However, if we're looking at complex numbers, there's more than one solution to this problem. Okay, so again, we're going to start by approaching this with writing 1 in terms of a complex number. Okay, so 1 is equal to, well, a modulus of 1, cis, and an argument of 0. Okay, again, if I was to draw a diagram for this, I'd end up with a length from the origin of 1, right here, and we're looking at an angle rotating anti-clockwise from the real axis, okay, anti-clockwise, an angle of 0. So we're just here. Now, there's a range of other ways that we can represent this point, okay, and this will help us find the other roots. So 1 cis 0 could also be written as 1 cis in brackets 0 plus 2k pi, where k is an element of the integers. So k can be 0, 1, 2, 3, 4, 5, 6, or it could be -1, -2, -3, -4. Okay, so there's a range of different values that k could be, and it would still always give us that same value of 1. Right? So, one way that we might look at moving forward from here is we're looking for the fourth root. So, in other words, we're going 1 cis 0 to the power of a quarter. Okay, so I could write it as to the power of a quarter, or I could write it as the fourth root. It's the same thing. And if I do this to these other scenarios, 1 cis 0 plus 2k pi to the power of 1 quarter, and I use De Moivre's theorem and say, all right, for De Moivre's theorem, I'm going to look at a power of a quarter. I'm using 1 to the power of a quarter. Okay, and then I'm going to multiply the power by this angle in here. Okay, so 1 quarter times 2k on pi is the same as 2k pi divided by 4. Now if I simplify that, I'll end up with 1 to the power of a quarter is just going to be 1. Then if I simplify the angle, I'll end up with k pi on 2. Now, remember what k can be. Okay? It can be any value, any integer. Okay? So 0, 1, 2, 3, 4, 5. Now, because we're looking at the fourth root, again, if we did a whole heap of them, you'd discover that there's actually 4 solutions to this problem. If it was the power, if I was looking at the fifth root, it's going to be 5 solutions. We could keep going and using all the different values for k, but what you'd end up finding is there's an overlap of solutions. Right? So if we just look at the first 4, we'll go 0, 1, 2, 3, 4. Well, that's even more. So 0, 1, 2, 3. And look at those solutions. So we end up with 1 cis, and if I have k is equal to 0, I'll get 1 cis 0. Right? My next one would be 1 cis, and if I make k equal to 1, it'll be pi on 2. Now, if I've got the next one where k is equal to 2, I'll end up with 1 cis pi. And the last one, if I look at k being 3, it's going to be 1 cis 3 pi on 2. Okay. Now, That's it, the solutions listed. However, this solution here is not between pi and negative pi, which we should make our argument equal to. All right, so this is 3 pi and 2. So if I was to look at a diagram of that, it's 3 pi and 2. So that's 1 pi. This is like 1.5 pi's. 3 on 2 is 1.5. So 1.5 pi's is here. Okay, so there's that point there. So another way that I could represent that is by saying, well, it's the same as negative pi on 2. Okay, so my 3 solutions are going to be 4 solutions are going to be 1 cis 0, 1 cis pi 2, and 1 cis pi, and the last one's going to be 1 cis negative pi on 2. Okay. Now, we could also express these in our Cartesian form. Okay? And if I was thinking about graphing each one of these, I'll go back to my graph. 1 cis 0 is just this point here. 1 cis pi on 2 is equal to this point up here. 1 cis pi is over here, and of course we just looked at this one. 1 cis negative pi on 2 is right here. Okay, so if I was to look at them in Cartesian form, we know it's a distance of 1 at each point. Okay, so our values are going to be just 1. Well, and that's the real component of it, so I could write it as 1 plus 0i if I really wanted to write it with its an imaginary component included. And 1 cis pi on 2 is this point up here. Now remember, this is my imaginary axis. This is my real axis. So that's going to be equal to 0 in the real direction. I'm not going anywhere in the real direction. But we've got 1 in the I direction, in the imaginary direction. Okay. Then after that, I've got over here, negative 1. So it's negative 1 in the real direction plus 0 in the I direction. And then, last of all, down here, we've got 0 in the real direction, and then negative I, which I could have just written as 0 take I. Either way, is there. I could simplify this further if I wanted to. You could also write it just simply as 1, and then I, and then this one would be negative 1, and the last one would be negative I. It's another way I could write it. All right. Now, if I was to graph this as well, I want to plot these on the complex plane. Well, I've pretty much done it over here, but probably should make it a little bit better than that. Not that this is the neatest diagram that you've ever seen, guys. Okay, so we should go length of 1, which is here, and it's that point there. My next one is going to be also in that length of 1, so it's at this point here. And over here, I've got negative 1 in the real direction, and over here, I've got negative 1 in the imaginary direction. So it's actually those 4 points are the points graphed on the complex plane. Right, thanks guys.